A lot of you are going to learn different techniques over the next couple of days, maybe in other classes, or may have learned techniques in other classes of what we're going to call definite integration. I'm asking you not to use those yet until we've earned the right to. And if you don't know what I mean, then great. I'm going to look at this graph, this arbitrary graph of f of x below. Its area between the curve is indicated by these rectangles. And I realize that many of you do not like the imprecise nature of how this works with these rectangles, but this is the best way we have at the moment to approximate the area. So think of this as we have these infinite number of these rectangles, and if I want to make this become a better approximation, I can always increase the number of rectangles. In fact, this delta x is referred to as the width of the different rectangles, and the area of each of these rectangles added up is a summation of all of these delta x's times the respective heights. In fact, you can essentially factor out the delta x, leaving behind this sigma where we are adding up all of the different heights. This sigma would just be the f of x1 plus f of x2 all the way up to f of x sub n. Now, we're going to replace this and use a little bit of calculus, because a calculus is essentially describing a limit process and saying that as n goes to infinity, meaning as the number of rectangles actually becomes an infinite number, then our rectangles actually start to look more like lines, like individual lines, and we're adding up an infinite number of those. So what calculus enables us to do is take this infinite number of things happening an infinite number of times and change this delta x into a dx, and this integral is really like a sigma. Think about it as the sum, and we'll think about this as an infinite sum, and this right here is of an infinitely small pieces of our function. So this process is really called the definite integral. And in this formula, this is really the formula for the area of a rectangle. The f of x is the height and the dx is the width. This is the definite integral from a to b, where a and b are called the limits of integration. Now, let's kind of move on to the next stage. When the function is greater than 0, meaning the function occurs entirely above the x-axis. So we'll just kind of write a little note here, above the x-axis. The definite integral can be thought of as finding the area under the curve. In other words, the area between the curve and the x-axis. So as an area under the curve, I can now just kind of do this by graphing, and that's what this is going to want us to do. If I graph the line y equals x plus 2, and I evaluate from a place of x equals 1, so this is x equals 1, to x equals 4, I know that the ordered pairs here are 1, 3, and 4, 6. So the area of this trapezoid, we can do this a little bit easier and just break it up into a rectangle and a triangle. The rectangle has an area of, this would be a width of 3 and a height of 3. And then this would be a 1/2 width of 3 times a height of, the difference between 3 and 6 would be 3. So I'd end up with 9 plus 9/2, or better yet, 27/2. 27/2 would actually be equal to the integral. The integral is the area under the curve. Another example of this is if I do an integral from -2 to 3 of the absolute value of x plus 1. You guys would be expected to know how to graph y equals absolute value of x plus 1 and have an x-intercept at -1, 0, a y-intercept of 0, 1, and go up with a slope of 1 on the right and then with a slope of -1 on the left. And if I went from -2, so -2, 1 would be an ordered pair, so we're just going to put a -2, 1, and then put an ordered pair here at 3, 4. Really what I'm looking for is this area between all that. So tracking down our different places, this would be -1, 0, and you can reason through that this is an area of 1/2, and this piece is an area of 1/2 width of 4 and height of 4. So you'd end up with the integral equaling 1/2 plus 8, or 17/2. Now, what happens when the graph dips below the axis? Well, let's consider this integral. And since f of x is less than 0, the height of your rectangle will actually be negative. This is going to occur when we have a function that looks like, let's just kind of do a little one, this. And so you have what we consider to be positive area here, and this is sort of like negative area there. That's the negative area. And if I do an integral from here to here, my positive and negative area could potentially cancel each other out. Let's look at this as an example on this next one. The integral from 3 to 5 of 2 minus x. So if I graph that, 2 minus x has a y-intercept of 2, a slope of -1. It's actually going to cross at 2, 0, and 0, 2. And if I'm going from 3 to 5, well, we're well beyond. This is 3 right here. And if I keep going, we'll call that 5. This is the ordered pair 3, -1. And this is the ordered pair 5, -3. My area here, we can calculate that as positive area, but my area is actually negative. So area would be equal to a 1/2. I'm going to do the actual area of a trapezoid. So 1/2 average of the, or 1/2 times the sum of the heights. So -1 plus -3, and then the width of that is 2. I get -4, and you can calculate that area of the trapezoid as 4. Just make it negative because it's going below the axis. So this is -4. Similarly, we can do the integral from 0 to 2 pi of sine of x. Sine starts at 0, 0, proceeds upward, crosses the x-axis at pi, proceeds downward, then crosses the x-axis again at 2 pi. And if I treat the area above and below, it should reason to you that those are the same area, and this integral would be equal to 0 since we have positive area above and negative area below. Continuing on, if I do an integral from -4 to 4 of 3 minus x, I could do, well, to graph 3 minus x, remember this is the same as the absolute value of x minus 3 by the properties of even functions. So x minus 3 would put this at, let's see, 3, 0, 0, 3. So 0, 3, 3, 0. And I want to go from -4. So if I plug in -4, I'm going to get 7. So -4, 7. And then 4, -1. 4, 1. So this is going to come down here and move up to 4, 1. And my integral would just be this area here with this area there. So let's actually evaluate that. Area is equal to 1/2. The base width was 7 and the height was 7. And then here I have 1/2, width of 1 and height of 1. So I get 49/2 plus 1/2. That gives me 25. Okay, the next one asks for a different kind of question. And this is, if you're paying attention and you're not muting this and just copying notes down, the area under the curve, when it talks about area under the curve, this is considered to be positive area. Whereas if I use the word integral, or if I show an integral can be positive or negative. So you're always going to see questions that talk about the area under the curve. Area under the curve is an absolute value. So think of positive area, or in other words, an absolute value. So the area under the curve between -2 and 3 of x minus 1, this is equal to the absolute value. Anytime you see area under the curve, we are referring to absolute value. And sort of an easy way to get at it is actually just to graph x minus 1. Put the ordered pairs down, -2, -3, and 3, 2. Drop these little lines down and just calculate the two areas, but add them up because they're going to be positive. Or alternatively, we can just bounce this up and make it actually be the absolute value, crossing all that out, plotting this point here at -2, 3, so that it actually falls into the absolute value function. And again, just calculating the two triangles and adding up their areas. This triangle would have an area of 1/2 base times height. This triangle would have an area of 1/2 base times height as well. So we'd get 9/2 plus 2, or 13/2. Area under the curve should always be positive, and it should always reflect what the absolute value function would have been. So probably the simplest way to think about it is if you see area under the curve, convert this into an absolute value function and just graph the absolute value function so you're absolutely sure about what you're doing. Sometimes converting things into absolute value is easier than you think it is. For instance, I'm just going to show on this graph, if I wanted to make this graph be an absolute value, then just everything below the axis would just get bounced up and made positive. This would bounce up and make positive, and this would be the area that I'd be discussing. But this is sort of a graph where it's not doing that. It's not necessarily doing that, and it's actually giving you the values of the areas under the curve. And I'm going to chop this one off right there at D because that's really, that's where that's hitting. So let's do the integral from A to 0. So A is on the left, 0 is on the right, and I get 3. The integral from 0 to C is equal to, well, this is going to be, this piece here is -4 because it's below the axis. And then this piece up here is +10. So -4 plus 10, and you get 6. The integral from A to B, if I go left to right, it's from here to here. I have a +3 and then a -4, so I get -1. Then you have the integral from A to C, so that's 3 minus 4, but plus 10, minus the integral from C to D, which is minus the -2. And then if I just simplify this, I get 9 plus 2, or 11. It wants the area under the curve from A to D. Remember, area under the curve is absolute value, so everything is positive. 3 plus 4 plus 10 plus 2, or 19. Number 8 says to set up the integrals necessary to find the area under the curve from sine from x equals 0 to x equals 2 pi. I want you to graph that and sketch it for a second before you kind of get at it. This is the graph of sine. So if I want the area under the curve, I could graph y equals the absolute value of sine of x, which is the same as sine. It's just that it gives you two of these little humps. And in order to set up the integrals, what we have to do is we have to what's called split the integral, meaning this is from 0, pi, and 2 pi. This is 0, pi, and 2 pi. And I'm going to ignore this for a second and look back at here. I want to force the areas to be positive. Well, the integral from 0 to pi of sine of x dx is already positive, but the integral from pi to 2 pi of sine x dx is going to be negative, and I want to force it to be positive without putting the absolute value on. I'm going to do that by just putting a negative here. If I subtract the negative area that it's already going to be, then I get this expression, which should end up being a positive number. This expression is actually equal to the integral from 0 to 2 pi of the absolute value of sine x dx. And several times over the next year and a half, you're going to ask me, how do you integrate an absolute value function? And I'm going to tell you, you have to split it up into a piecewise. So this would be the correct answer for what the question's asking. The integrals necessary to find the positive area under the curve. Your calculator has a built-in function to evaluate definite integrals. I'm not going to go into this. You can pull this out and kind of do it, but these are the places you go. It's in the calculus menu and underneath the integral section. Or if you're using the 84, you just need to press alpha. If I can spell the word alpha. If you're using a TI-84, you can just alpha F1, and then it brings up the menu of options, and you should see the definite integral there. It's pretty common. It's also in the menu. Okay, then this is another common one. It says consider this piecewise function consisting of 4 line segments and a quarter circle. So usually when I get things like this, I like to just drop these lines down and start plotting in my areas. This is an area of 1, 2. This one goes with this, so that's 1. This is 1. This whole thing should have an area of 4. This is a quarter circle of radius 2. Pi times 2 squared over 4 would be equal to pi. That should just have an area of pi. This piece here would have an area of 1. I kind of drop these down. This is an area of 2. 1, 2, 3, 4. This is an area of 4. Okay, then we can answer these questions. The integral from -4 to 0. So we always read these integrals from low to high, which means left to right. So -4 to 0 is 4 plus pi. 0 to 4 is going to be this 1 right here. Oops. But then -2 minus 4. So I'm just going to write this as 1 minus 2 minus 4. That's -5. Then you have the integral of the absolute value, which means everything gets added as positive values. 4 plus pi plus 1 plus 2 plus 4. So that is 11 plus pi. And then finally you have this thing, which should not be confusing, but it tends to be. And I want to avoid any confusion on this, meaning this is going to be the same thing as this plus 2 is what's going to throw you off. This is going to be the same thing as the integral from -4 to 4 f of x dx plus the integral from -4 to 4 of 2 dx. This right here we get from the graph. We're going to tell what this is based on what the graph is doing. But this is going to be on us to figure out what's going on. So the graph -4 to 4, we actually did that, but we didn't do it completely. We have to consider negative areas. So that's going to be 4 plus pi plus 1, but then -2 minus 4. And I'm going to add this next piece here. And this next piece, for right now, we're going to have to graph that. So graphing y equals 2, I'm just going to graph it. It's going to be a rectangle from -4 to 4 with a height of 2. That area is 8 times 2. That should be 16. So my final for this should be 4 plus 1 is 5, minus 2 is 3, minus 4 is -1, plus 16 is 15. I should get a 15 plus pi. Okay, there is a part 2 of this, so watch the second video as well. You again are welcome to kind of pause and work on the first part of the assignment and then get to the second video. The second video, I'm pretty sure, addresses this idea too, that if I have the integral from a to b of f of x dx, that's equal to the opposite of the integral from b to a. If I switch the limits, it switches the sign around the thing. But we'll deal with that in a little bit here.